See, I am giving you, it will clear your all concept for exam. I am making these 3 problems. One figure is like this, made up of 2 straight conductors of infinite length and 1 circular. Second figure is like this, 2 straight infinite length conductor and 1 semicircular part. Third figure is like this, 2 infinite straight conductors and 1 semicircular but of this shape. We want to calculate at this point, it is center. We want to calculate magnetic field at O. In this case, O is at this point, center of that complete circle. If we make complete circle, its center is O. In this, current is moving in this direction, the value of current is I. In this, current is moving in this direction, coming from this way, going back. Same in this. What they are saying, straight conductor, straight conductors are of infinite length. And radius of circular part is R and current is I. So these are 3 cases, A, B and C. We want to calculate magnetic field. At O. One by one we will discuss at A. You need magnetic field at center of semicircular coil. What we did when we were calculating for this, we used Biot-Savart law. First we took one small element. After applying Biot-Savart law, we got magnetic field at center mu naught upon 4 pi IdL. In this case, sin theta was 90 degree because length will make always an angle 90 degree with radius. So sin theta was 90 degree. IdL sin theta by r square. We take small so many portions and all magnetic fields were in same direction. By adding all field, we get total magnetic field, means it was common portion mu naught upon 4 pi r square. We take summation of dl. We are calculating for one turn. So what we get there? There we get mu naught Summation of all lengths means 2 pi r by 4 pi r square. Cancelling r with r, 2 pi with 2 pi, we got there mu naught upon 2r into I. I is also there, I. For n turns, we say it should be mu naught and I by 2r. This was the way we calculated in 12th class. But in half circle, in place of sigma dl, we will put pi r. If we will put pi r, means it will become 4 mu naught ni upon 4r. It will become mu naught ni upon 4r. Getting my point? So we will use this concept. So what we are saying, for semicircle, magnetic field should be, for one turn, mu naught I, it is in place of 2 pi r, it should be pi r upon 4 pi r, 4 pi and this r square. So we will get this formula, mu naught I by 4r. Getting my point? So now we are going to calculate magnetic field in first case. Since O point is in line with current, so for first part we are making 3 parts. It is first part, it is second part, it is third part. We will calculate for all and we will add if they are in same direction, or we will do vector addition. It is first part from where current is coming, it is second part and it is third part. And in this case, it is first part, it is second part and it is third part. See, what happened in first part? First part is in the direction of point is on that conductor only. So for first part, theta is 0. If theta is 0, what is the Biot-Savart law? I dl sin theta by r square. Theta is 0. So for first part, magnetic field should be 0. Second part, it is semicircular. What is the direction of magnetic field? You can imagine, if current is this, is going in this direction, use your right hand, this. You want to calculate magnetic field at this point. What I told you, curl your fingers in the direction of current, where your thumb is indicating inside. It means the magnetic field is inward. What is the formula? Formula was mu naught I by 4r. For inward, this symbol we are using. We use always this symbol, means invert the paper inside. Again, for this part, current point is behind the conductor. So theta is 180 degrees, sin 180 is again 0. So for A case, we got magnetic field mu naught I by 4r and direction is inward inside the paper. Magnetic lines are going inside the paper. Now we will go for B part. We will go for B part. For first conductor, conductor is of infinite length and point is near at one end. So what we saw, if point is near one end, mu naught upon 4 pi I by d. Mu naught upon 4 pi I by d. D is R. So I by R. What should be the direction? If you put your thumb in the direction of current and fingers towards that point like this, current is going this. So magnetic field is upward. So it should be in upward direction. For upward we are making this figure. In place of cross we will put dot. It is the symbol for upward magnetic field, means lines coming out from the page. For second portion, current is in anti-clockwise direction. Again it is outward the page. This thumb is indicating towards outside the page. So what should be the formula for that? Magnitude is this, mu naught. If you want to add, multiply and divide by 4 pi. So mu naught upon 4 pi I by R. Again direction outside the page. For third, current is going this. If I am putting this, again magnetic field is coming outside. So same, mu naught upon 4 pi I by R. All are in same direction. So vector, if we want to vector addition, we can add simple. Denominator is mu naught 4 pi R. Take mu naught upon 4 pi R common. What you will get? I we can take common. So 1 and 1, 2. 2 plus 4 pi. 2 plus 4 pi. You can take 2 common, cancel this 2. So 2 plus 2 pi, 1 plus 2 pi. What is in case of C? First portion is like that only, which was there. So same, mu naught upon 4 pi I by R. And it is again outside the page. Dot means outside the page. Second, magnitude is same, but direction, what is the direction now? Now current is in clockwise direction. Current is moving in clockwise direction. In that way it was anti-clockwise. So now it should be like that, inside the page, first case, inside the page. So what we will write? Mu naught upon 4 pi. 4 pi I by R, inside the page, plus, again this is same as was in B. So mu naught upon 4 pi I by R, outside. Now two magnetic field are outside and one is inside. Which is greater than 4 pi R in denominator? It is 1 plus 1, 2, and it is 4 pi. 4 pi is greater than 2. So final magnetic field will be inside the page, And if we are taking the sign outside positive and inside negative, if we are writing, no way we can write. So we will write that. So we are taking 2 times mu naught upon 4 pi I by r. It is outside and inside means in opposite direction. It is opposite means we have to show minus. Minus we are given for inside. So it is mu naught upon 4 pi I by r. So take mu naught upon 4 pi I by r common. You can take 2 also common. So what you will get? 1 minus 2 pi. Direction is inside. Means this. So I think you got the all concepts for direction. Now you will not do any wrong problem in exam. Directions are mainly important in this chapter and not a big rule. Your right hand rule is there to support you. So after that we are moving towards force on a conductor. We will write here for semicircle. In this we note for semicircle. So we are writing here so that you can remember this. For semicircle they can use in exam. Magnetic field will become half. In place of mu naught and I, by 2r, you will get 4r at center. If one turn is there, you can remember this formula separately. Mu naught I by 4r. Mu naught I by 4r. We multiplied by pi, numerator, 4r was there. So in the numerator it should be pi only. It should be pi only. In this only we multiplied by pi, 4 was there. So we multiplied by pi only. So it should be not 4, it should be pi. It should be pi. In this case also, mu naught I upon 4r. In this we multiplied by 4 was there with pi only. So not 4, it is we cannot 2 minus pi. So we cannot take this 2 common. So it should be 2 minus pi. 2 minus pi. So in this way we can solve this problem. Getting my point? So take care of sign mainly. Next. Now we are going to discuss force on a moving charge in a magnetic field. Force on a moving charge in a magnetic field. In a magnetic field. It is known as Lorentz force. It is Lorentz force. If Q charge with velocity v entering in a magnetic field B at an angle theta, it will experience a force which is given by Lorentz force, and it was Q v cross B. In vector it was F Q v cross B. It means it is Q v B sine theta. If particle is coming at 90 degree, in that case it will become QBV, because sine 90 is 1. This force QBV sine theta, it will provide centripetal force and particle will start moving in a circle. If it is coming at 90 degree, you can take QBV. And in this case, that centripetal force will become mv square by r is equals to QBV. If it is coming at theta, you have to put sine theta here, 1 also, this. So what we can calculate? Cancel 1v. Means radius you will get by the formula mv upon qb sine theta. mv by qb sine theta. mv is linear momentum, so you can write it in terms of energy 2m E, where E is the kinetic energy. Also you can do one thing, velocity you can get from this 2 pi r by t. If particle is taking t seconds to complete one circle, its time period is t, then you can remove t by this, and in this case you will get r is equals to m into 2 pi r divided by t qb sine theta. R will be cancelled out and you will get the formula for t. T is equals to 2 pi m by qb sine theta, and reciprocal of t is frequency, so frequency will be qb sine theta divided by 2 pi m. Now we will discuss force on a current carrying conductor. Force on a current carrying conductor. So you have complete derivation in your 12th class with the help of Lorentz force. We have calculated this. Force on a current carrying conductor. It is ILB sine theta. Means if I current is flowing through a conductor of length L, which is placed in a magnetic field B, making an angle theta with magnetic field, you will get this formula ILB sine theta. You will get this ILB sine theta. So this is a force on a current carrying conductor. What should be the direction of force? You can calculate by Fleming's left hand rule. Fleming's left hand rule will give you the direction of this force. What left hand rule is saying? Stretch your forefinger, central finger and thumb perpendicular to each other. If Forefinger is representing the direction of field. Forefinger, F for field, F for forefinger. C for central finger. It is if representing the direction of current. Thumb, M, M for motion. Motion should be in the direction in which we are applying force. So thumb will represent the direction of force. If we stretch our left hand's thumb, forefinger and central finger stretched like this, central finger is representing the direction of current. Forefinger is representing the direction of field. Thumb, M, will represent the direction of motion, means direction of force. It is very important for what we are going to discuss now. I have two conductors. What I want to discuss, force between two current carrying conductors. Two current carrying conductor. No magnetic field is there. What will we do now? See, one conductor is this, one conductor is this. Suppose I am taking current is flowing in same direction. Two cases we will take, I1 current in this, I2 in this. Same direction. First we will discuss this, second we will discuss this. When current is in opposite direction, what will happen then? Generally they are asking this, in which case wires will repel each other, in which case wires will attract each other. We want to discuss this thing. See, this is an infinite length conductor. It will produce a magnetic field. What should be the magnetic field? Nearby this conductor, second conductor, due to first conductor. Take your right hand. Put thumb in the direction of current. Fingers pointing towards the point where you want to check magnetic field's direction. It is inward. Means magnetic due to field due to first conductor. It is inward. Now, your second conductor is in a magnetic field. It will experience a force because it is current carrying conductor in a magnetic field. In which direction it will feel force? We will use Fleming's left hand rule. Now I am using my left hand, stretching my forefinger, central finger and thumb in this way. Field is in downward direction, means inside the page. Central finger should be in the direction of current, where thumb is pointing towards first conductor. So it will feel a force toward the first conductor. What should be the magnitude of this force? If I am calculating force per unit length, force per unit length is I into B. Theta is 90, so only I into B. I is I2. What is B? B is magnetic field due to this conductor. We know the formula. Mu naught upon 4 pi to I by R. I means this current because magnetic field is due to that current only. If distance between these two conductors is D, it should be I1 by D. So what we are getting? Symmetrical result, mu naught upon 4 pi. Both currents are involved, I1, I2. With same manner, now we will check in what direction first conductor will feel force. Now, that magnetic field is due to I2 current. Now I am using my right hand again. Thumb in the direction of current, fingers pointing towards the point where we want to calculate magnetic field. Line coming out from palm is outward, means magnetic field is in outside the page. So I am making this, it is the direction of magnetic field now. Direction of magnetic field is this. Now we will use Fleming's left hand rule. Field is outside, forefinger should be outside. Central finger should be in the direction of current. Direction of current outside the page. Where thumb is pointing towards second conductor means it is experiencing a force towards this. So if both are experiencing a force towards each other, means they are attracting each other. Force will come same because it was symmetrical result. So it means if in two wires current is flowing in same direction, they will attract each other. Generally students are confusing with the same. What they learn, same nature pole repel each other, same nature charge repel each other, but not correct for this situation. If current is flowing in same direction, wires will attract each other. If it is in opposite direction, it will repel. So in this case, wires will attract each other. Means wires are attracting each other. Getting my point? So this was very important formula. कि wire will attract in this case, and in this case wire will repel each other because you will get force in this direction. So it is attraction. Here repulsion is taking place. So it was very important. Now we will use this concept of force in galvanometer. What is happening in galvanometer? Same thing we are using there. Galvanometer. What we are doing in galvanometer? We put one coil in a strong magnetic field like this. When we pass current through this coil, what will happen? Coil is suspended with the help of a wire. Suppose it is north pole, it is south pole. It is the direction of your magnetic field. Current is flowing through this wire, this. So what will happen? This is your coil. Your this wall is north pole, your this wall is south pole. Current is coming downward in this. In which direction this arm will feel a force? Fleming's left hand rule. Forefinger should be in the direction of field. Central finger in the direction of current, outward. So this arm AB feel and force in outward direction. Outward direction means in this direction. Since in this current is in opposite direction, so force in this will inward. So if two arms of a coil are experiencing a force in opposite direction, one outward, one inward, so they will rotate the coil. These two arms are parallel to magnetic field. Theta is 0, so sin theta is 0. So no force on these two arms, only these two arms will experience a force. If length of wire is L, if this length is L and width of this is B, the force will make a torque, and torque should be F or F sin theta, theta is 90, so we are taking F into this B. If it is B, it is B. What is F? F is IL B magnetic field sin theta, theta is 90 degree. If there are n turns, force will become n times, n type. So what we are getting, L into B is area, I B N, I B N into A, it is torque. But what will happen then if there is a twist in the wire with the help of which this coil is in magnetic field? This twist will try to open the, means one couple will develop in this wire which will try to open the twist like this. If couple per unit twist is C and total twist is theta, so C theta in the equilibrium position should be equal to I, B and A. So what we are observing here, I is equals to C upon NBA theta. Since for given galvanometer, wire is fixed, so C is constant, N is constant, B is constant, A is constant. So this is known as galvanometer constant. What it is known as? Galvanometer's constant G. And that I, we can write this CNBA, it is galvanometer constant. So I is proportional to theta. With the help of theta, you can calculate the strength of current. After doing some arrangements, we are converting galvanometer into ammeter and voltmeter. You know that use of ammeter to measure the strength of current. If you want to measure the strength of current, you have to put this galvanometer on the way of current, so that whole current will pass through it, and you are able to measure what current is passing through it. But if whole current will pass through the coil, it can damage the coil. So we are doing some little arrangements. We are putting one shunt. Shunt means a low resistance wire parallel with galvanometer, and we will allow only current which is sufficient for full scale deflection in galvanometer. Remaining current will pass through this shunt. If you want to measure I current, what shunt you needed, we can calculate. Since S and G are in parallel, so potential difference for both should be same, but V is I into R. So Ig into G is I minus Ig into S. So if you know your instrument, what current you need for full scale deflection and what current you want to measure, you can calculate the value of shunt. When you are using this operator, this galvanometer, to measure the potential difference between 2 points, means I converted the galvanometer into ammeter. It was now ammeter. Means this whole system is known as ammeter. Galvanometer plus shunt. This full instrument is now ammeter. If you want to measure potential difference between 2 points, this is resistance R and you want to measure potential difference across it, V. We know that what is V? I into R. So we want whole current should pass through this so that we will get actual value of I into R. But to measure this potential difference, we need one instrument. It is again working with current only. So we need some current for deflection. It should be minimum so that actual voltage we can get here. So we will allow only current which is sufficient for full scale deflection. To blocking rest current, we are putting a high resistance in series with this G. Now these two are parallel with this. So potential difference across these two should be equal to V. So what we are getting? V? Ig into R plus G. If you know what range voltmeter you need, V. What current is required for full scale deflection? You can calculate the value of R by this formula. So now it is voltmeter, and it was the principle of voltmeter. Ammeter, voltmeter and galvanometer. They can ask numerical on any one. They can ask numerical on any one. So after this, now we will start our crash course assignment of 45 questions.